Hi everyone, so we're starting our unit on graphing trig functions. In this unit we're going to graph all 6 trig functions and 3 inverse trig functions. And there'll be a little more to say about inverse trig and its uses. But for right now, I'd like to start with you filling out this t-chart. You should be able to tell me what the sign of 0 is, and the sign of pi over 2, and the sign of pi, and so on. So why don't you pause the video and take a couple of moments to fill this out, and we'll go from there. Okay. Yes, 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 yes. Those are the values I got. Now, what am I going to do with this? Well, let's take a look at graphing this information. Okay. So we've got 2 pi and 4 pi, pi, 3 pi. Okay, so 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, 2 pi 0, 5 pi over 2, 1, 3 pi 0, 7 pi over 2, negative 1, and here 4 pi. Now, if we play connect the dots, we're going to have something that looks like this. And that's a graph of sine. Now, you could just keep putting values in here, right? That means this graph is going to go forever in the positive direction, but also in the negative direction, and just going to continue like a snake serpenting down. Now, my question for you is, here's our graph of sine. I'd like to know what the domain is. I'd like to know what the range is. Can you tell me? Remember, use interval notation. That's right, since this goes forever in that direction and in that direction, we say that the domain is all real numbers, and I would say I would prefer you to write that as negative infinity to infinity, especially if you're headed to calculus. The range, these are all the possible y values. Well, it looks like my lowest y value is negative 1, and my highest y value is 1, and the function actually attains those values, so we're going to use bracket negative 1 to 1. Now, there's another word we need to define here, and we're going to be using that word a lot in this unit, and that word is period. So, how far do we have to go before this graph starts repeating itself? In other words, after I get to here, I've done one cycle of the graph, and now I'm ready to do a second cycle. How long was one full cycle of this graph? Well, it went from 0 to 2 pi. And by the way, when we talk about period, we're not going to say the period is from 0 to 2 pi. Now, period is one number. It's not from here to here. Period is the distance from here to here. So 2 pi minus 0 is 2 pi. The period for sine is 2 pi. We go 2 pi before we start repeating ourselves. Okay? We're going to be talking about period a whole lot here. All right, so with that in mind, let's think about transformations. I don't want to get to that. But first, maybe it would be worth our time to see our other reference graph, cosine. And please take a moment to fill out all the cosine values for these angles, okay? I'd also like to revisit domain and range and see what happens with that. But yeah, pause the video. It might take you a minute to do this. Hey, welcome back. Did you have 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1? Me too. So we're going to start here at 0, 1. We're going to go down to 0 at pi over 2, hit the bottom at pi, and then back up again. Plonk it down, plonk it up, plonk it down. And 5 pi over 2 is 0, 3 pi is negative 1, 7 pi over 2 is 0, and 4 pi is positive 1. Oops. There we go. All right. So, what's the domain of the red cosine graph? Well, just like sine, I could just keep putting numbers in. So we're going to have negative infinity to infinity. Usually, students are asked to graph 2 periods of a function. Now, you could certainly graph this one from 0 to 2 pi and from 2 pi to 4 pi. Some students like to do the 0 to 2 pi, but also the negative 2 pi to 0, 1. Yeah, I don't. This would be my 2 periods, 0 to 4 pi. But in anything that I created for you, worksheet, quiz, test, all that stuff would just be graph me 1 period. 1 period of cosine. 1 period of sine. Okay? You'll do a couple of problems, I hope, where you do 2 periods. Places like the U of A like it when you do 2 periods. Okay. So the domain stayed the same. What about the range? Is the range still negative 1 to 1? Yeah. These are remarkably similar functions. They have the same domain, they have the same range. What about the period? How far do I have to go with the x's before I start repeating myself? Ooh, I'm at the high point here. I go to the low point and back up to the high point where I started at 2 pi. So again, the period for cosine is going to be 2 pi. In fact, you might even notice that if we just pushed this graph over a little, and how much a little? Well, to go from here to here, I just need to subtract pi over 2. Then these graphs would sit on top of each other and look identical. That's why they're co-functions. Sine and cosine. They're just transformations of each other. Okay. Yeah, that's it. Here we go. So, oh, by the way, all those points, yeah, you need to be able to graph them. In fact, let's go back to sine for a moment. 2 pi, 4 pi, pi, 3 pi. Sine starts on the midline, goes to the high, back to the midline, down to the low, and back to the midline. There's 1 period, goes high, back to the midline, down low, back to the midline. And there's 2 periods. Oh, by the way, we call this midline that runs through the graph the sinusoidal axis, aka midline. Okay. Yeah, when I think about this, I think about, gosh, there are lots of points here. 7, 0, 0, 5 pi over 2, 1, 3 pi 0, 7 pi over 2, negative 1, and 4 pi 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow, that's a lot of points. 9 points. You know, when we think about these trig functions, we can write them just like we wrote functions last semester, where we said, okay, y equals a sine bx minus c plus d. We can have that same framework that we talked about with transformations last semester. Well, I guess it was last year. But with 9 points, ooh, that's a lot of transformations to do. I mean, remember last semester? It would always be 3 points. Yeah, I don't mind applying transformations to 3 points, but 9 points? No. That is not a good thing. So I can say that one of the reasons why I ask my students to graph one period is to cut this down to 5 points. But even 5 points to apply transformations to, that's still going to be almost twice the work of last semester. So again, I'm not really keen to do trig graphs using transformations. I'm going to show you another way, all right? I will say, though, that when we do inverse trig graphs, I'll be using transformations because we'll be going back to having only 3 points. Okay. So let's, before we get to graphing things, let's please talk about what each of these letters would do to the graph. Okay, this is outside the function. Does it affect x's or y's? Oh, it affects y values. Nice. And this has a name. It's called the amplitude. And the amplitude, right, we're going to multiply all the y's by this number. The amplitude is that distance. The amplitude is that distance. And amplitude is always positive. And what I mean by that is if you see -3 sine theta, the amplitude is 3. What does the negative do? I'll show you in a little bit. That's a transformation. But the amplitude is always the absolute value of that number. Amplitude is a distance. It's how far up we go from the midline, how far down we go from the midline. So the amplitude in this problem, or with this function, y equals -3 sine theta, this function has an amplitude of 3. And what we'd be doing is taking the regular y value and multiplying it by this. Oh, okay. So if my amplitude were 3, then I'm going to have 1 times 3, or 3, and 3 times -1 is now -3. So this a value, just like last semester, is a vertical stretch for a greater than 1, or compression for a less than 1 but greater than 0. Okay, and that negative, well, that negative in this situation we know is going to multiply all the y's by -3, and that's just going to be a reflection. We're multiplying the y's, so it's a reflection across the x-axis. And here we'd have pi over 2 -3 and 3 pi over 2 +3. The amplitude would be 3 in either case. All right? So A stands for amplitude. Amplitude is the distance from the sinusoidal axis, or midline, to the high or to the low. Okay. What about B? What do we know about B? Well, this is inside the function, so we know the x's are being affected by this. And what I'm supposed to do is understand that B is a horizontal compression, like you're playing the accordion. A horizontal compression for B greater than 1, and a horizontal stretch for B between 0 and 1. And that's kind of the opposite that we just had for amplitude, isn't it? For a greater than 1, we had a vertical stretch. And for a between 0 and 1, we had a vertical compression. Okay, so we've got stretching and compressing. And this is inside. So we know that, one other thing about B, and this is actually going to be new and important for us. B plays a role in period, right? If I'm stretching the graph this way or compressing the graph this way, then the period changes. So we're going to have a formula. You'll often see it as period equals 2 pi over b. So I'm going to take whatever b value is given to me, and I'm going to do 2 pi divided by that number to find out the period. So if I'm looking at y equals sine 3/4 x, here's my b value, and I want 2 pi over 3/4, which is going to be 8 pi over 3 for the period. Now, normally my period goes 0 to 2 pi. Well, in this case, I might be going from 0 to 8 pi over 3, which is more than 2 pi, but less than 3 pi. Don't worry, we'll talk about graphing that shortly. Okay? In addition to this equation, the rewritten version of this equation will be useful when we do the going backwards problems, where I give you the graph and I ask for the equation. In that case, we're going to want to know what b is, and if I multiply both sides by b and divide both sides by period, I get this new formula, which is great for going backwards. Okay, we'll use this. When we go to graph the function, we're going to use that. Okay, C, horizontal shift, D, vertical shift. All those transformations can work, and some teachers ask their students to do that, but really, I'd like you, as I've been saying all year, to have a great graphical sense, and to have a great graphical sense is going to require you to have to do as little work as possible to get a fairly accurate graph, okay? All right, so let's talk about y equals to sine pi x minus pi over 3 plus 5. Okay, so this, and if I have to graph, we'll do 2 periods for this first one. If I have to graph 2 periods, that means I've got to write down 9 reference points and apply these transformations? No, not gonna do it. Okay, so if I'm not going to do that, what am I going to do? Well, I think I would be happy to show you. So, step 1, set the argument, i.e. the stuff in parentheses, equal to 0, 2 pi, and 4 pi to find where this graph starts and ends its period. Okay, so what does that look like? Well, we've got pi x minus pi over 3 equals 0. Pi x minus pi over 3 equals 2 pi. That would be sufficient for one period. But if we have to do a second period, then we'll also want 4 pi. So let's solve each of these equations. Pi x equals pi over 3. And if I divide both sides by pi, we get x equals 1/3. And here, this is 6 pi over 3 plus 1 pi over 3 is going to be 7 pi over 3. And if I divide by pi, I get x equals 7/3. And over here for my second period, this is where the second period is going to start. It's also where the first period ends. And this is where the second period is going to end. So that's 12 pi over 3 plus 1 pi over 3 is 13 pi over 3. And if I divide both sides by pi, I get x equals 13 thirds. So period starts here and ends here. Second period starts here and ends here. All right, well, let's see what that looks like. One third, 7 thirds, 13 thirds. Okay, so second step. Second step is going to be find the quarter points. What do I mean by quarter points? Well, I know that halfway in between 1/3 and 7 thirds is 4 thirds. How did I know that? Well, this midpoint is the average of these. 1/3 plus 7 thirds equals 8 thirds. Oh, I'm averaging. So I'm dividing by 2. 8 thirds times 1 over 2. These cancel, and I get 4 thirds. Okay? In fact, I think to speed this process up a little more, when the denominators are the same, all I have to do, add the numerators, double the denominator. So 8 over double this, 6. Hey, 8 over 6. It's a lot faster to have the common denominator, add the numerator, double the denominator. Okay. So, but I didn't want just halfway points like that and that. Add these. 7 plus 13 is 20. 20 over 6. Oh, that reduces to 10 over 3. I actually want to know not these half points only, but I also need to know the quarter points. So this one, this one, this one, this one, this one. Oop, not that one. We stopped it. So let's do it again. Add the numerator, 5, double the denominator, 5, 6. Add the numerator, double the denominator. Add the numerator, double the denominator. Add the numerators, double the denominator. And if you want, you can put them all into 6. I don't have any problem with this, so I'll just use this. So what do we know? Well, we have all the quarter points. The period starts here and ends here. Second period starts here and ends here. Well, let's draw that. Now, what was it? Oh, I guess step 3, draw in sine shape. Now, what was the shape for sine? We started on the midline. We went up to our high point, back to the midline, down to the low point, back to the midline. And so there's one period. Second period starts on the midline, goes to the high point, back to the midline, down to the bottom minimum, and back to the midline. And here's our second period. Okay? Yes, you do have to know how to graph that. You do need to know that shape. But this is 2 periods. And I'm hoping Mr. Claus will usually ask you only for 1 period. Great. 2 steps to go. We're almost done. We've drawn in the shape. 4. Label the sinusoid axis. Okay, so I know that there are teachers both at UHS and at Catfoot who, instead of doing what I'm going to show you, do this other thing. They have the student graph this here, and this is the x-axis. And then they make the students for the plus 5, regraph this whole thing up here, shifted up 5 units. I think that's crazy, and I fully understand why in the old days mathematicians were occasionally asked by the community to drink hemlock tea and kill themselves. Because that's just wacko. No. I want you to label the sinusoidal axis with your d value. So our d value is 5. So this is not y equals 0. This is y equals 5. Y equals 5 is the sinusoidal axis. Come on, you know that's a fun word to say. Okay. Yes, that really was step 4. I'm just going to label the sinusoidal axis, the midline through the graph. Now it's y equals 5. Aha! Now, isn't that a lot better than having to regraph this thing higher up, 5 places up? Oh my goodness. I mean, talk about a waste of your time. Finally, step 5, we'll use amplitude to determine high and low y values. And how will we do that? Well, our amplitude is 2. So 5, and this is 2. So 5 plus 2 means this part here at 5, 6 will have a y value of 7. And here at 11 pi over 6, 11, 6, will be 5 minus 2 for 3. This point here at 17 sixths, this point will be 5 plus 2 or 7. And here 23 sixths, the y value will start at 5. We'll go down to 5 minus 2 is 3. These should always be the same. These should always be the same. Okay? That's it. That's the fully graphed thing. And you will be able to do this in the same speed you were able to graph with transformations last semester. So, but in order to get us to that place where you're really comfortable with these 5 steps, a couple of things have to happen. First, you need to remember the shape for sine. Starts on the midline, goes up, back down. There's 1, period, pi, 2 pi, 0. And yes, I do still need you to label those points on the graph. There's our sine reference graph. And our cosine reference graph. Cosine starts high on the y-axis, goes down, down to be down, even further, and then back up, and finally, at 2 pi, we have a value of 1 again. Okay, I always feel like this kind of looks like the outline of West Virginia, or some sort of steer. Okay, so these are our 2 reference graphs. We're not going to be using transformations, but we do need to be able to draw the correct shape in. Oh, and I don't know if you noticed, but if I draw 2 periods of this, 2 periods of this, remember, look remarkably like 2 periods of that, just shifted. So keep in mind, these are, in fact, co-functions, which is why we'll see that relationship. Generally, though, when we graph only 1 period, cosine's always going to look like that steer's head, and sine is always going to look like this. Yeah? All right. So next, I would love it if we could talk briefly about these. Y equals a sine x. And what I want to know is, what does that do to the graph of sine? Here's a graph of sine. Sometimes we use theta, sometimes we use x. Doesn't really matter. And it's not sine times x, it's sine of x. I'm throwing stuff into sine. Okay? All right, so what does that do? We just talked about it. This is amplitude. It's a vertical stretch or compression. And here, y equals sine x plus d. Well, this is outside the function just like this is outside the function. So this one's the vertical shift. Y equals sine x minus c. Remember, inside is opposite land. That's a horizontal shift. Okay? Sometimes c is a positive number, so if c is 2, x minus 2, we're shifting the graph 2 to the right. But c could also be a negative number. What if c is negative 2? Then we have minus, a minus 2, or plus 2, and we know we're going to go left 2, just like last semester. And then we've got y equals sine of bx. Again, this is inside the function, so we know this b affects the x's. And even though I see multiplication here, I know inside is opposite land, I'm going to be dividing by these x's, and that's going to cause my graph to horizontally compress for b values greater than 1, and horizontally stretch for b values between 0 and 1. Nice. What about these? What do these do? What can you tell me about these? Y equals negative sine of x, and y equals sine of negative x. Do you remember these? What do they do? This is me multiplying all the y's by negative 1, and it is going to be a reflection, and many people got reflection across what wrong on the last quiz we had about that. So if I'm multiplying all the y's by negative 1, my original graph then will flip across which axis? This is a reflection across x axis. Yeah, and yes, I'm multiplying the y's by negative 1. And here, this is inside, so it affects x's. I'm dividing x's by negative 1, which causes us to reflect across the y-axis. Now, here's the thing. We often, because this graph goes on forever, we wouldn't ever actually notice that reflection across the y-axis, because the graph would just sort of be doing what it was doing before. We'll see this sometimes. We'll see it more because we generally restrict the domain. 1 period, 0 to 2 pi. 2 periods, 0 to 4 pi. Okay? And then when we have this, yeah, we'll definitely see that, the effect of that negative. Just like we would see the effect here with negative x plus 4. Yeah, I'm going to subtract 4 from all the x's, but then I'm going to divide all those x's by negative 1. And so my graph is going to go whee from 4. Yeah, so good. Keep that in mind. All right, let's get to doing some practice then. Y equals 2 sine x over 4 plus pi over 2 minus 3. Here it is. I got to do those 5 steps. Do you remember what those 5 steps were? Well, first one was, that's very good. First one was set the argument, the stuff in parentheses, equal to 0. And let's just do 1 period, 0 to 2 pi. Okay, so x over 4 plus pi over 2 equals 0. and x over 4 plus pi over 2 equals 2 pi. I will ask you to be careful about this next step. The most common mistake that students make when graphing sine and cosine is not something that they learned in trigonometry. It's the fact that they can't solve this equation. And why? It usually has something to do with the fractions. You could, of course, multiply everything by the least common denominator to cancel out those fractions. Yeah, I'm not going to do that. I am, though, going to subtract pi over 2. Have x over 4 equals negative pi over 2. And then I'm going to multiply both sides by 4. So x equals negative 4 pi over 2, or negative 2 pi. Oh, okay. And what about this one? Well, I'm going to subtract pi over 2. And that's going to be 4 pi over 2 minus 1 pi over 2 is 3 pi over 2. And if I multiply both sides by 4, I get x equals 6 pi. So my period starts at negative 2 pi and ends at positive 6 pi. That's what we were doing with step 1, finding the starting and ending points for one period of our graph. Okay, and so for us, they occur at negative 2 pi and positive 6 pi. Good. So there's negative 2 pi, there's 6 pi. Remember, step 2 was find the quarter points. Okay, so first we find the point halfway in between. We average 6 and negative 2. And that's going to be 4 over 2, or 2. So this is 2 pi. Oh, I guess these have pi's attached. There we go. And you know, one way you can check this distance and this distance should be the same. So the distance from negative 2 pi to positive 2 pi, that's going to be 4 pi. The distance from 2 pi to 6 pi, 6 minus 2, it's another 4 pi. If these numbers aren't the same, it's probably that this number is wrong, and you should go back to where you averaged these endpoints to get that number. Okay, so we've got our halfway point, but I need quarter points, so I'm going to do it again. I'm going to average negative 2 and positive 2, that's 0, and I'm going to average 2 pi and 6 pi. Remember, I'm adding two numbers, so I'm dividing by 2. This is going to be 8 pi over 2, or 4 pi. Oops, 4 pi. And again, look, from here to here is 2 pi, from here to here is 2 pi, from here to here is 2 pi, from here to here is 2 pi. I have seen some teachers do an approach where they say, find the starting point and the ending point. No, they actually just find the starting point. Then they find the period, right? They do that thing where we know that period equals 2 pi over b. And in our problem, b is 1/4. 2 pi over 1/4. And so our period is 8 pi. Okay, so if I find the starting point and add 8 pi to it, I get to the ending point. That's good. Well, and these other teachers say, now we want these quarter points, so I want you to divide this period by 4. And that's how much we're going to go up by each time. And sometimes that can be useful, but I've watched students using both the method that I showed you about finding quarter points and this method of taking 1/4 of the period and using it. And in general, the students who do the 1/4 of the period thing, yeah, it takes them a lot longer. I'm not sure why. You can use it if you like. Well, I would ask Mr. Paz if he's okay with that. But yeah, no, I wouldn't recommend it. Step 3, draw in the sine shape. Remember, sine starts on the midline, goes to its high point, back to the midline, down to its low point, and back to the midline again. And please, sine does not look like that. Please don't do that. Please don't do that. Concave down, concave up. There's our sine graph. Okay? Step 4, label the sinusoidal axis. So for us, the sinusoidal axis is y equals -3. That's step 4. And then finally, step 5. With step 5, we'd like to use the amplitude to find high and low y values. In particular, this point is going to be d plus a. And this point is going to be d minus a. So let's say that our a value is 2 and d is -3. So we're at -3 and we add 2. -3 plus 2 is -1. And that was 0, -1. And here at 4 pi, well, I'm at -3 and I'm going down to -3 minus 2, and that's going to bring me to 4 pi -5. And I'm done. All right? Okay, 3 more. Y equals 1/2 cosine 2x minus pi over 6 minus 5/2. All right, so what am I supposed to do? Step 1, I'm going to set 2x minus pi over 6 equal to 0. And what else for one period? Good. 2x minus pi over 6 equals 2 pi. So now solve those equations. 2x equals pi over 6. Hey, some people make the mistake right here. So if you turn out to be one of those people, the fix for it is show the work. It works every time. Pi over 6. And now I need to divide the x's by 2. You can do it like this, but I would just say like that is fine. So pi over 12 is where our period starts, and 2x minus pi over 6, we've got it here. We'll add pi over 6 to both sides. Yes, I do need a common denominator. This is 12 pi over 6 plus 1 pi over 6. I have 13 pi over 6. But that's what 2x equals. So let's divide by 2 and have x equals 13 pi over 12. All right. And does that make sense? Look, the distance from here to here, 13 pi over 12 minus 1 pi over 12 is going to be 12 pi over 12, or pi. The period here is pi. Does that make sense? Well, think about it. Normally, the period for sine or cosine is 2 pi, but here, because of this b value, I'm going to divide everything by 2. So while we used to have a period that went 2 pi, now we're getting a period that only goes pi, because we squished the graph horizontally by dividing all the x's by 2. Okay? So our graph is going to start at pi over 12 and end at 13 pi over 12. So let's plot those points and draw in our shape. Plot points, draw in shape. Okay, so we were at pi over 12 and 13 pi over 12. Oh, find quarter points is what I meant to say. So halfway between these, well, Add the numerator, 14 pi, double the denominator, 14 pi over 24. Now, I'd like to have these be common denominator, so if I can do some simplifying here to get a common denominator, yeah, I'm going to do that. So I can take a 2 out of both of those and get 7 pi over 12. The distance from 1 pi over 12 to 7 pi over 12, yeah, that's 6 pi over 12. And the distance from 7 to 13 pi over 12, again, that's another 6 pi over 12. So just a quick check to confirm that we found the right quarter points. It's really a waste of your time if this is wrong, because then the rest of them are wrong. Or if this is wrong, because then really everything else is going to be wrong. And that'll make you sad as well as make me sad. Okay. But we need to find quarter points. So cut it in half again. Add the numerator, 8, double the denominator, 8 pi over 24. You could reduce that to 4 over 12 so that they can all be 12s. You could reduce that to pi over 3 if you want. I don't care. Whatever makes this easier for you. Most students like to see common denominator. But sometimes that's not going to be convenient, and let it go. Don't worry about it. 8 pi over 24. Happy camper. Remember, we want accurate, but also fast. Add the numerator, 7 plus 13 is 20, and double the denominator. Yes, you could reduce that to 10 pi over 12. Or you could just as well leave it as 20 pi over 24. I think, though, with 10 pi over 12, I can see that these distances are all going up by 3. Right? From 1 to 4 is 3, from 4 to 7 is 3, from 7 to 10 is 3. So I'd like to be able to see that too. And that's something that we're only going to see if we have that common denominator. Okay, we found those quarter points. Now we need to draw in the correct shape. This is a positive cosine. Cosine starts high, goes to the midline, down to its minimum, and then back up again. Like that. Now I will say that there are a number of students who, even though they know this is where the period starts, they do this other thing. Let's talk about this really scary thing that these students do. Please don't do this. They start here on the y-axis because cosine starts high. And then they get this, and their graph looks like that. And I don't know what to tell you because that don't look like it's supposed to. That could be one period. No, that could be one period of cosine. But that's not ours because ours has to go to here. Oh my goodness. And there are these other students who, even after they find these points, do stuff like this, where they don't actually have the critical event happening at the quarter point that they wanted. Hey, I don't have that x-intercept. I don't have that x-intercept. I don't have that x-intercept. What are you doing? Stop doing that. Okay? What we need is to remember, that when we find that pi over 12 and that 13 pi over 12, that's where cosine starts. Cosine starts high here, not on the y-axis. There's been transformations. We're not starting at 0 anymore. We're starting here. Okay? This was 7 pi over 12, 4 pi over 12, and 10 pi over 12. You start high, go to the midline, go low, and back up again. Please don't make the absolute value shape here. Concave down, concave up, concave up, concave down. There's cosine. So, step 3, we drew in the shape. Step 2 was really find the quarter points. Okay, step 4, label the sinusoidal axis. There. Now, because you're labeling this here, I don't need you to label this point 4 pi over 12 negative 5 halves. I mean, you can if you want, but I don't need it because you're telling me that over here by labeling the sinusoidal axis. That's step 4. And step 5 is to use the amplitude to help us determine where these high and low y values are. We know the x value here is pi over 12, but what's the y value? Well, it's going to be d plus a. So negative 5 halves plus 1 half is negative 4 halves. You could write negative 2, sure. And here, we're at negative 5 halves, and we're going to go down 1 half. Negative 5 halves minus 1 half is negative 6 halves, or negative 3. Don't forget to label that as an ordered pair. Okay? And then this one has the same y value over here, 13 pi over 12, negative 2. Ta-da! There's our graph. 1 period. Trust me, it gets even faster. Okay? Why don't you try this one? Why don't you see if you can graph this one? Y equals negative 3 cosine x over 2 minus pi over 4 plus 7. Okay? And just like last semester, I think it's going to be helpful for you to think about what these transformations are doing to see if, in fact, what happens makes sense. Okay? So, how's that going? I hope you paused the video and just come back now from that. If not, no, really, you should step up and try that. Pause the video and give it a go. Okay, step 1, we're going to set the argument equal to 0 and equal to 2 pi. So I get x over 2 equals pi over 4. If I multiply both sides by 2, I get x is pi over 2. And here, when I add pi over 2 to 4 pi over 2, that's 5 pi over 2. If I multiply by 2, I get x equals, now I'm tempted to cancel these and write 5 pi, but then they don't have a common denominator. So I'm going to use 10 pi over 2, because now they have a common denominator, and I know if this is where my graph starts, and this is where my graph ends, halfway in between, 1 plus 10, 11 pi, double the denominator, 4. Okay, now this isn't going to reduce in any kind of friendly way, but I really want these to have common denominator, and I really want these to have common denominator. So I'm actually going to write this as 2 pi over 4 and 20 pi over 4, because now I can add these together and double the denominator, 13 pi over 8. I'm going to add these and double the denominator, 31 pi over 8. Good. Nice. Yep, it's very easy to make mistakes with these. Throws the rest of your graph off. Please be careful. Now, cosine normally starts high. This negative multiplies that y value by negative 3, and so now I'm starting down here. So negative cosine has this shape, whereas positive cosine has this shape. Okay? They're just reflections of each other. But no one's going to tell you, hey, watch out for that negative. That means I start low, go to the midline high, and then back down again. Okay, so we found the quarter points. We drew in the shape. I kind of want to now say that this is y equals 7, my midline. And now finally, let's use the amplitude. The 3 is the amplitude. I'm going to go up 3. 7 plus 3 is 10. And if you want to reduce any of these, now's a good time to do it. I'm not going to. Here, at 2 pi over 4, the y value was 7, but wait, we went down 3 from there. So 7 minus 3, 2 pi over 4, 4. And here, 20 pi over 4 is the x value. The y value here is 7, but we're going to go down 3. Here we went up 3. Now I'm going down 3. So 7 minus 3 is 4. All right, there's my well-labeled graph. How about we do one more? Or better yet, how about you do one more? Y equals 1/3, negative 1/3 sine of pi over 2x plus pi over 4 plus 5/3. Hot dog. So, take a couple minutes, pause the video, come back when you're done, and we'll talk about this one. But really, you should definitely try this one. This is going to be 8 pi over 4 minus 1 pi over 4, 7 pi over 4. And I end up with, let's cancel, 7 over 2. Okay, here's where the period starts, here's where the period ends, and I have a happy common denominator. So we get x equals negative 1/2, and x equals 7/2. Okay, so put those on that number line. We're starting at negative 1/2, we're ending at 7/2. I'm not drawing the y-axis in, because often what happens is this doesn't pass through x equals 0. And then students have made it an extra critical point. Yeah, don't do that. Just find halfway between these. 7 plus negative 1 is going to be, but don't forget, you want the average of that, right? So that's, 7 halves minus 1/2, 6. Yeah, I do want to do that. And that's going to give me 3 halves. So, midway, 3 halves. The distance from here to here, from 3 to 7, is 4. From negative 1 to 3 is also 4. So, what's the quarter point going to be? Well, if I add these together, I'm going to get 2 halves, and I double the denominator. That's 2/4 or 1/2. And here we'll have 5 halves. Good. Now, look what happens. You do this, and suddenly the student says, and guess what? Sine is supposed to start and end on the midline. And I'm not doing that, because now I've included this point, which is in fact not one of our quarter points. These are our quarter points. Draw this. Don't do this. I mean, you can do that, but a lot of kids who do that make all kinds of mistakes, adding all kinds of extra points to the graph which don't exist where they think they do. All right, now this is a negative sign. Positive sign starts on the midline, goes up, and back down, and up. So what does negative sign do? Well, negative sign goes from the midline to the minimum, back up to the maximum, and then on the midline again. So here's our negative sign shape. Okay, this is y equals 5/3. And here, I'm going to have 1/2 common left. Well, 5/3 minus 1/3 5/3 is this y value, minus 1/3 is going to be 4/3. And 5/3 plus 1/3 is going to give me here a y value of 6/3, or if you like, 2. And there's my graph. All right. Well, I think it would be nifty keen if Mr. Paz gave you a quiz on this tomorrow. So you go to class today and practice it, and tomorrow he gives you a quiz. That'll be good. Okay, everybody. See you in the next video.